excuse me, on the, sorry, I'm dealing with YouTube stuff. Okay, there we go. I see myself counting down on the live stream. Okay, we are here now. QRP Service Monitor. It's a project I've been working on. We've already got 2 videos in it. There's a playlist in the link below, and I need to mute my thing. There we go. Sorry, this is a crummy start. I gotta learn. Do you even YouTube, bro? Anyway, Service Monitor. So we want to be able to test things. Go look at the links below. I link to the Ham Radio Workbench podcast where we talk about what it is that we're building, and also the previous videos where we actually did some of the circuit layout and the board layout, or the schematic layout and the board layout. And but at the end of the previous video, I did not have the energy to go and do a bunch of the silkscreen work. So that's what we're going to be picking up today. A couple of things that have been going on in my life really quickly. My good friend Exploding Lemur bought me a new toy. He decided that what I needed in my life was a PDP-8. And so he bought me a PyDP-8, which is a PDP-8 front panel simulator board that has a Raspberry Pi on the back that's running an emulator of the PDP-8. I haven't finished assembling it all yet, or the soldering is done, but I haven't put together the OS image on the Raspberry Pi, and I haven't started playing with the assembly yet, but I intend to. That was one of the other things I was thinking about doing today, but decided to do this stream instead. So in the grand philosophy of what's on your workbench, that was something I was working on yesterday. I'm pretty happy about. Yeah, that's it. Let's get started. So I'm going to go switch to this screen. Quick refresher on what we're talking about for the QRP Service Monitor. What it is that we're trying to do is we're trying to build a piece of test equipment that you can hook up to a radio that you're building and use it to kind of measure the health of your radio. And your radio is 2 different things, right? The transmitter and the receiver. So part of the bits in here will be designed to measure your transmitter, and part of them will be to measure your receiver. So most of what we've got on this board are all transmitter bits. So your radio comes in, they got 2 different connectors, whether it's BNC or SMA, because different people use different connectors, and so we just have both connectors in parallel. Either you can use either one. And then if you want to hook up your signal to something with a high impedance like an oscilloscope, well, you can tap right here. I got a 10K in series just so that you don't accidentally short out your radio through that connection. Your oscilloscope's going to have like meg or 10 meg ohm input impedance, so hopefully that 10K won't affect it, or if it does, it'll affect it in a measurable way and you can compensate for it. But other pieces of test equipment have low impedance inputs, like spectrum analyzers, or like an SDR or something like that. So here is a pad, minus 50 dB pad, that will present a 50 ohm impedance here, but 50 dB down from the sample port there. And so you can look at your input signal coming from your radio that way. So I'm not actually trying to recreate those, but I am making it easy to connect to them. And then internally, we have a connector here that's just kind of another high impedance tap for a frequency counter, which I haven't built yet. But you can get cheap and easy modules from eBay that you can plug in there, or we will be designing a frequency counter that will integrate with all of this. So all of that is in the input. There's a relay here that will switch between whether the input port goes through the directional coupler and out to the output ports, or whether it gets connected to a signal generator. And the signal generator input up here is what we're going to be using to test the receiver on the radio side. Haven't designed that yet, but we've got a port for it. These 2 diodes here are just to protect the signal generator if for some reason you accidentally have this relay triggered over to the receive side, but you accidentally key up. The signal coming from your transmitter will short out through those diodes into ground. You're possibly likely to blow out your transmitter, but at least you'll save the signal generator. Anyway, then we have a directional coupler here that we're going to be using for measuring forward and reverse power. Each of those taps go into these logarithmic op amps. Basically, it's a RF signal in here and a DC voltage out here that tells you the amplitude of that RF signal coming in. It's a neat little chip called the AD8307. We've got two of them, one to measure forward and one to measure reverse. Keeping in mind that we are not measuring the actual power through, we are measuring the sampled power going through the directional coupler. So we're measuring forward and reverse individually. We also have a tap on these inputs. The main reason for that is, well, it might be interesting to be able to look at the forward and reverse power individually. I did have someone respond to me on Twitter as to they had a very good reason why they wanted to be able to look at these signals, and I can't remember what it is, but we have them. But the other reason is that it gives you the opportunity to not bother populating all of this over here and instead use another one of those cheap eBay modules. You can get this chip on a module for they're about $10 or $15, I think, from eBay. And so there's a little SMA port that you can use to just connect those together. If, for example, if I screw up this design, we'll be able to feed off of that sample port and go straight into the measurement. But assuming you're on our board, then the output of this is it's an unknown impedance. I couldn't remember exactly what it is. So I just stuck an op amp on the output here in voltage follower mode, just as a buffer, and we have it on both the forward and reverse. So these are the outputs. The DC voltage here, it's like 0.02 volts per dB milliwatts, and then there's a Y-intercept point. I can't remember the exact details, but it's all there. You measure the DC voltage here, and that'll tell you how much power is coming in from the forward and reverse. And these chips have an amazingly wide dynamic range. So they should be able to measure very weak and very strong signals. So that's how we're measuring forward and reverse power. On the output, we have another relay here that switches between either your antenna port, so these, again, an SMA and a BNC, so you can use either one on the back panel, or it will go to an internal one, which will be connected to a dummy load. I thought about putting a dummy load directly on the board itself, and I may actually still do that. I don't know. I gotta go look at the board itself. But by having this an external port like this, it allows you to get the heat away from the rest of the system. You can mount a board to like the chassis and use the chassis as a heat sink, or mount the heat sink on the outside or something. I don't know yet. But in any case, you will be able to connect it to a dummy load internally or to an external port. Then we have connectors. TX, RX, ground. Those aren't used anymore. I used to have one big connector there. Delete block. I used to have a bigger connector here that had all of the signals coming in and out, but I decided to split it out and put the connector for these relays right next to the relays themselves. That way I'm not having to run traces all across the board to a single big connector. I don't mind having multiple cables. So we got a 6-pin over here that's just used for powering all of these chips and for measuring the forward and reverse power. You'll also note that everything over here is on a digital ground, where everything over here is on a signal ground, and everything that goes across them are through these capacitors. So the RF ground and the digital ground are separated. They are not shared. Similarly with the relays, the coil voltages on the relays are completely isolated and go through the connector. They're effectively digital ground, although it's not connected on the schematic. So the point being that the RF ground is completely isolated from the rest of the signal. So in a nutshell, that's what we're doing. So let's go take a look at the board. So I actually did a lot of the board layout last time. You see these little pigtails. That's because they connect to ground planes. But let's make the ground planes go away so they're easier to see. So inputs are over here. Here's the BNC and the SMA. I don't mind having them next to each other because you're only likely to ever use one at a time. Although I think my idea was to have you only populate one at a time because they are awfully close together. You wouldn't really be able to populate both of them and use one or the other. In any case, here are the radio inputs. There's the relay that switches it between the signal generator input or to the directional coupler. Here are my taps. We've got the high impedance tap here that goes to a BNC because I figured the most likely use case there was going to be an oscilloscope, and they're all BNC. Or a low impedance tap like an SMA. My thought here was that I am likely to use an SDR, like a SDR dongle or something for my low impedance tap. So I put an SMA on there because they're all SMA. But here here's the 50 dB pad, and then here's the internal frequency counter tap. So these are all the radio connections over there. There are the protection diodes for the signal generator. Why did I make those physical diodes and not surface mount? I don't know why I did that. This is surface mount. Huh, okay. Anyway, so there's the diode, there's the directional coupler, a couple of toroids with some other fancy windings going through it, and then there's the relay on the output. Again, here's the antenna connectors and the dummy load. Oh, I did make that externally accessible. Okay, that's fine. And then on the directional coupler side, the forward output of the directional coupler, here's the sample port for it, and then here's the logarithmic op amp I was talking about. You'll notice that I've got separate ground planes. Here, let me go ahead and draw the ground planes again. So the red over here, and there's this giant black line, and the only signals that ever cross that black line are through those capacitors. And those capacitors are going to be doing DC blocking functionality, and as long as they're a high enough voltage to be able to handle whatever ground differential you have, it should completely block. It should allow all AC signals to go through, but it should completely block DC coupling between the two different grounds. In here is all the RF ground, and out here is all our digital ground. So we have these caps just to kind of allow return currents. Kind of don't like that there. That should be going this direction. I'm going to turn that around. But then the like here's the signal paths. Anyway, so primarily we've got a whole lot of text all over the board, and we need to clean that up. I have a thing that I like putting values on my board, not references, because values change, or well, because I hate having to look up documentation while I'm assembling a thing. The reason you do references is because they your values may change over time, and that's a perfectly valid reason to do that. But I like doing it this way. And it's my board, so I'm going to move them around. And if Kenneth were watching right now, he would be going, "Oh my God, Mark, why are you doing this manually? Why don't you just modify all your parts so you don't ever have to do this again?" And he's got a totally valid point. But, and I don't have an answer for it because it's a lot of parts, and I don't always know which ones I'm going to be using. So, yeah. So, reference D4, move that over there. What is that? Oh, that's the diode designator. Okay. So if anyone is watching right now, go ahead and throw any questions or comments in the YouTube stuff, the chat channel. Always happy to chat and accept heckling from peanut galleries, that kind of thing. Unfortunately, this was a very last-minute stream, so my normal peanut gallery are all busy doing other things today. Hi, Kenneth. Hi, Nick. How you guys doing? Jeremy liked my Twitter post about it. I don't know if he's going to make it. He didn't say anything about whether he would be coming or not, or joining us for the peanut gallery. Isn't this exciting? Something that is exciting. I've actually recently started a club in my area. I live near San Luis Obispo, California, on the central coast of California, kind of halfway between San Jose and Los Angeles. And we've got some clubs locally, but they tend to be oriented for specific things. So like there's the Cal Poly Amateur Radio Club, of which I am a very proud alum. So that is W6BHC, and they're a great club. They do a lot of cool things, but they're really kind of targeted toward college students. Go figure. It's a college club. And, you know, college students go away during the summer. Field day happens to be during the summer. They're just kind of optimized for different variables than what I'm looking for in a ham club. Similarly, we have what's called SLOEC, SLOW ECC, which is the Slow Emergency Communications Council, I think is what it stands for. And they are our local Aries Races group. Again, very good group. but they are really targeted toward MCOM and all of that fun stuff. It's much less. They'll occasionally have talks about technology, or like I went to a meeting. It was about someone brought in a portable repeater and showed how repeaters are built and that kind of stuff. And it's very good club, but again, kind of targeted for different things. And so I wanted a club that was targeted more toward the things that I'm interested in. And I've been talking about doing this for a while and never got around to it because round tuits are hard. Even square tuits are kind of hard to find, but they're around somewhere. Anyway, I never did anything until not long ago. I thought of the perfect name for the club, and that was really kind of what opened up the floodgates on giving me the motivation to go out and make it happen. And the name I came up with, yep, there is one right there. The name I came up with is CQ805, which I'm kind of proud of. 805 is our area code. There it is. And I'll confess, I kind of borrowed the idea for the name from the DEF CON groups, right? Because there's DC 303 and stuff like that. And that makes much more sense for hackers where, there's a big carryover, a crossover between hacking and phone phreaking uses area codes and blah, blah, blah. So that makes a lot more sense there. So I kind of borrowed that. We already have the SLOEC group. Their club call sign is W6SLO for San Luis Obispo. So I kind of didn't want to go with slow for anything because it just would have made the call sign confusing. And it's also a wider area than slow. I actually don't live in San Luis Obispo. I live right outside of San Luis in a place called Arroyo Grande. But San Luis Obispo is our county seat, and it's kind of the area name, right? It's kind of like Silicon Valley or LA. Even if you don't live in LA, people think of you as living in LA. I don't live in San Luis Obispo, but people think of it as San Luis Obispo. But 805 is much bigger than that, right? And it's kind of indicative of trying to find people in the area, not San Luis Obispo specifically. I would welcome anyone from anywhere, really, whether you're in SLO County or not, actually. And we do have several members of people who used to live here but don't anymore, but still kind of have an affinity to the area. And it's just, a club. And hopefully we're going to be doing some cool stuff. So anyway, CQ805. Oh, and then the CQ is kind of a indication that I want to be inclusive. I want it to be perfectly frank, not a bunch of old white dudes, right? Old retired guys. And I kind of want, there are a lot of people I know who are hams, who have licenses, but don't really feel, I don't want to say welcome. Welcome isn't the right word, but the groups that are there aren't really targeted toward them. And I want something that is welcoming to everybody and inclusive of everybody. And I know that those other clubs like SLOEC would welcome anybody who wanted to join, but they're not really targeting their activities to the kinds of things that other people are interested in. And so I wanted to make a place where people were welcome to come and do whatever it is that interests them. And so I'm actually kind of targeting it as more of a forum to find other people who have like interests and connect with them, whatever that interest is, and kind of enable the connecting of people with common interests. That's kind of where I'm headed with it. Anyway, CQ805 is the club, and it's been something I've been putting some effort into lately. I have a website, but it's just a placeholder right now, CQ805.radio. Unfortunately, CQ805.com is an Asian gambling site. I was going to register CQ805.org, but org is not common enough that I was worried that people would accidentally type in .com by default and end up in the wrong place. I figure CQ805.radio is different enough and specific to our use case enough that it would hopefully have fewer accidental type-ins to .com. So, yep. Right now, it's mostly Slack channel. I haven't set up a mailing list yet. That was going to be one of the other things I was thinking of doing today, but I decided to work on this instead. But a lot of good conversations going on. We had kind of our first quote-unquote meeting. It's more of a meet-up yesterday at lunch where people were asking, so, DMR, how does it even? And so 10 of us went out to lunch yesterday, and I kind of gave a primer on DMR, what you need to know to get started, without going into a lot of the nitty-gritty details that aren't immediately relevant. I mean, they will be once you start programming your radio, but it's the stuff that I was trying to do was more of a, this is what you need to know if you're going to do DMR. And it seemed to be pretty well received. Okay, let's see if we can, I want to do this. You know, obviously you would have to ask the members to see whether they agreed with me or not, but I think it was pretty well received. Okay. Give me a zone, and I want to bring that over there by 2. That'll give us space. And then that one. Every time I say that one, I have to do it in Captain Jack Sparrow voice. A better one. That one. That one? Aye, that one. Okay. And we do B to redraw ground planes, and then let's turn on the ground plane and see what that looks like. Whoa, that is very green. Okay, there we are. Yeah. What? No. I'm actually thinking about taking that and moving it there. That would be better for that ground reference and that one. But unfortunately, actually that wouldn't be too bad. I also haven't done any stitching, have I? Yeah, I'm going to move that. I think I'm going to do the same on the other side as well. So let me undo these changes because I actually want those back to where they were. And then I'm going to take that one and put it right there. And then redraw those. Can I do the same thing here? Do I want to do the same thing there? Come on. Dang it. So my grounds are there. Huh. Oh no, that's the op amp. There's the other one. Yep, I do want to do it there. Okay. Come on. Okay. Yeah. Yep, I think that's what I want. Okay. Turn off our ground planes. Let's go look and see if we left any other text anywhere on the board. I'm not seeing it. Alrighty-o. Let's put that on the correct layer. We want that on front silk. 0.6, yeah. 6 and 0.001. I think that's right. And then we'll rotate that and put that there. Dummy load. moth just tries to dive bomb me. Dummy load, and then we'll put that there for antenna. What did I call that? Radio? Yep. Okay. That resistor's right on top of that, isn't it? Phooey. Okay. Moth keeps dive bombing me. High Z tap. Minus 50 dB. Actually, you know what? Hold on. No, we'll just do that. Yeah, we'll keep it like that. Phooey. Really? All right. I'll put you under. Radio. Oh, hey, I can do it this way. SMA. I hate that hitting enter doesn't actually close that dialog. I want it on the thing. Yep, okay. And then dummy load. I'm going to put that down here because that's where everything else is. Oh, but nope, 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 nope. Left. Okay. What is this? Freak counter. There we go. Okay. Yep. SIGGEN. Okay. This is forward. I think. Let me make sure I don't have those backwards. So if I select that, that should tell me which one it is. That appears to be the reverse. Yep, okay. According to my schematic, that is the reverse. Okay. So all the connectors are labeled. Just kidding. We got the pin connectors that still need to be labeled. To digital deck. Okay. Okay, let's right justify this, and I want to make that a 4, 5. We'll do that. What? Just decided not to. Okay. Here. Why are you not redrawing? That is so weird. Okay. Um. Actually. Okay. So those are my inputs, and what did I say here? This was 100 microfarads. We'll do 100 microfarads. I want to center justify this. Okay. Hmm. Oh, okay. I was trying to figure out what I was doing here for my decoupling, but that's a 22 in series with 5 volts. Okay, that makes a lot more sense. Okay, so I'm going to put that there. We are going to left justify it. Edit 22 ohms. And that one is a 0.1 microfarad. You know what? I might need that to be a 1 microfarad. Because if I've got that series, I'd have to do the math to figure out where that's going to cut off. Okay. So we got 3 people who claim to be watching the stream right now, according to YouTube, but no comments. If you're watching this stream, I would love to hear a comment from you, even if it's a peanut gallery kind of comment. All right, 1 nanofarad and a 2K to ground. All right, which one's which? Not that it really matters, but that's a 1 nanofarad on the outside and the ground on the inside. What about that one? That's a... Okay, so caps on the outside, resistors on the inside. Okay, we can do that. Not that it matters all that much. Edit, nanofarad. Nope, nanofarad. What? No. There we go. Okay. So I'm getting these values not from my memory, but because I am looking at the schematic here. And so, you know, the power was at 22 in series with 5 volts to the power line into the op amp with a 0.1 microfarad. I think I made the call on the fly to change that to a 1 microfarad, just to make sure that it'll roll over at a lower frequency. Whoa. Why are you losing it? Anyway, wow, that's weird. And then a 1 nanofarad and a 2K to ground. That's also going to that's going to double as a low pass filter here. So that's going to be shunting any RF that might be coming out of here to ground through that 1 nanofarad. So, and then we got a similar filter up here for each of the 8307s. So they each have their own little RC filter on power. I'm going to change all of those to 1 microfarads. Yeah, okay. So let's get back to work. All right. But I already have that. Right there. Similarly. Right there. AD8307, is that what I said? 8307, yes. Boop. Okay. And then what are the capacitors on the inputs? 51 puffs? Yeah, 51 picofarads on both of those. And then the ground is a 1 nanofarad. Okay. Oops. Looking at the wrong one. But the design is the same. Okay. So, where's the 1 nanofarad? There it is. That's going to overfill. Yep, it's too big. So those are hundreds for my 50 ohm to ground, and then what's that? That's a 100K in series. Okay. 100K in series. say 100 ohm to ground. There we go. Okay. And then do all the same things, but in the reverse order. Edit 51 picofarads and center justify that. And then 1 nanofarad. Okay. Did I move that closer? I think how did I do it down there? No, I don't have to do it that way. I'm going to give that more space. Okay. Oh, no, okay. 1 microfarad. 22. Okay. So 22 ohm into a 1 microfarad into the power on the 808307s. We got 51 puffs for the block for the pass into those. That value seems low. Okay, well, we'll figure that out. I can replace those on the fly. And then a 1 nanofarad to tie the grounds together. Then a 100K series. Oh, because it's 100K and the 51 puffs. That is the... all right, let's do math. Oh, nope. Yes, I use BC for math. So 100,000, it's 1 over 2 pi RC. 1 over 2 times 3.14 times R times, what did I say, 51 puffs. So that's 51 millifarads, microfarads, nanofarads, picofarads. 1 over 2 pi RC is going to give me a 31 kilohertz cutoff. And this is a series, 51 puffs in series with 100K, so that's going to be a high pass. So if I'm there it is. If I'm doing my math right, come on, there we go. 1 over 2 pi RC, 1 over 2 pi R is 100K, C is millis, micros, nanos, picos. So those are my picos, 51 picos. If my math is right, then at 31 kilohertz is going to be the cutoff, and since that is a series capacitor, that is going to be high pass. So that's going to high pass at 31 kilohertz, which means it should pass all of the RF spectrum. Okay, I think I'm comfortable with those values. So let's actually do the same math for the 22. Come on. So 1 over 2 times 3.14 times R times, that's millis, micros. So that's 1 microfarad. And that's going to be 7 kilohertz. And so that's going to be because I'm shunting to ground, so that's going to be a low pass. So that's going to filter off anything above that frequency to ground. And if I use the original value of 0.1 microfarads, it's going to do the same thing at 72 kilohertz. I don't see a reason not to go lower. Like even that 31 kilohertz, if I replace those with 100 puff caps. No, I think 51 puffs was an important input impedance on those chips. So I think I want to stick with the 51 puffs on that. But the bypass, I do want to go down to like 7K. So yeah, I'm going to keep those at 1 microfarad. 1 microfarad will do 7K. Yeah, okay, good. If you have any questions about what the heck I just did, let me know, or the math I was just doing. I'm happy to go over that in more detail. All right, so those are our components on the DC side of things. Now, let's go over to our pads and look at these. And we'll do, oops, I do want edit, center. Okay, that's a 10K. Wait, what? There we go. Okay. That was weird. Okay, what are the values around my pad? So that one's a 10K. On the input to the pad, and then I got a 4.7 to ground. Not a 4.7K, a 4.7. And then a 47 in series. And how am I going to specify the... $10K, 10K, 4.7, 47. Okay. And then a 10K there. And there's nothing else up there. But I do have the diodes. Okay. I gotta put those on the bottom side too. And flip that. And we'll put that there. And we'll do edit. Diode. There's another one there. Whoop. Too close. There we go. And then, oh. Flip it back over here. Okay. What is K1? G5V-1. Okay. G5V-1. That's the type of relay. Okay. So I want the bigger font for this one, and this is Ant Dummy. So Normally closed on this one. So we're over here. Normally closed is the antenna. I don't think I have enough space for that over here. No, okay. So the slash antenna, active low is on antenna, dummy load is on high. I'm not sure I like that. Maybe? I don't know. I'm not super happy with those designators, but it'll do for now. Okay. Now, the most important text of all. What is this? Nah. Creative Commons, non-commercial, share alike, attribution, share alike. RF Deck version 1.0. Okay. One other thing I need to do. That's as good a place as any for it. Put that on the front solder mask. Whoa, whoa. Okay, there are my fishies. Fishy, fishy, fishy. What are the diodes? Or not the diodes, the toroids. Oh, there's a... Ideally, I would put some instructions on the board about how to wind those toroids. Oh, I have it over there. So, confession is that I have stolen this design almost 100%, well, at least the RF side of this design, from the Noga Watt. The Northern Georgia QRP Club did a watt meter, or QRP watt meter, and this is their design. You'll see some pretty similar, transmitter comes in here, goes directly across through this toroid out to the antenna. And then the windings on this toroid, one side goes to ground and the other one goes over to this thing here, but it goes directly across the toroid over to this one with a winding to ground, yada, yada, yada. This RF section here is exactly the same as what I've got on my board. The difference is that they are using diode rectifiers and an LC circuit here. So the diode rectifier into the inductor over there and the capacitor to ground. The two of these make a low-pass filter, and they end up rectifying the RF coming from the forward and reverse taps, and they turn that into a DC voltage over here that you send through a potentiometer just to kind of calibrate your meter, and then into a meter. And the idea being that you have a 1 milliwatt or a 1 microwatt meter. I think they need a 1 microwatt meter, and it just goes to a analog meter, panel meter, and that's how you measure the RF power. There's a better view of the schematic, so this should look awfully familiar. And I kind of ripped off this schematic almost whole cloth, except that I kind of cut it off right here, and I ran it into the 8307s instead. So rather than using diode rectifiers, because the diodes put a lower limit on how much power it can reasonably measure, because you need to have enough power to be able to get across the forward voltage drop on those diodes. And whereas the 8307s don't have that problem. They're able to measure power down to a much lower level. Okay, so this is what I needed. FT50-43 cores. So the 43 is the type of material. It's a magic number. It's some scientist somewhere came up with it. Whether it's like 6 is a common material, 2 is a common material, 43 is a common material. And the 43 is the one that kind of seems to be most commonly used, or very commonly used in HF toroids when you're trying to make a transformer out of a toroid. 43 is a very common material. It has good saturation properties for the entire HF band. I have no idea. Don't ask me to explain why 43 is good beyond what I just said, but it does seem to be a very common FT or ferrite toroid material used. 50 specifies the size. And so there are calculators you can use. I think toroids.info is a very common one to use. Anyway, between the size of the toroid and the material of the toroid and the number of turns, you can very accurately kind of predict how the toroid is going to act. And so if I remember correctly, this watt meter is designed around this particular toroid, that material on that size, and then if it's 7 turns to 1 turn, what is the turns ratio? Diodes prior for the toroids wind 7 turns on each core, being sure that both are wound in the same direction, and then remember that 1 turn means once through the hole, and then The primary will simply be one wire passed through the center of the wound toroid, and it will be added after the other winding. So you have a 7-to-1 turns ratio on this toroid, and that is what ends up making it's a transformer is what it is. And so the 1 turn of the RF passing through it and the 7 turns around gives you a 7-to-1, or is it 49-to-1? Anyway, it gives you an increase. I think it's a square of the number of turns. So I think it ends up being like a 49-to-1, almost a 50-to-1 increase in voltage, but a decrease in current, and it's a tap. It's weird. I don't pretend to understand exactly what's going on here. Somebody who knows way more about this than I do can explain this better than I can. Point being that that's the toroid we need. So what I'm going to do is I'm going to put text on the page that says FT50-43 FT50-43 7 turns on the little ones, and then just one. Okay, 7 turns. So we'll do that. Actually, I'm going to do it on both of them because they are the same. And then show me all the front silks. Okay. So that just puts the silk artwork on top of the copper. I don't know. Got to be a better way to describe what we're trying to do. All right, we may just have to write instructions for this. But the idea being that the 7 turns go to these 2 here, and then this one is just a straight through. Okay. All right. Let me try something. See if I can do this without embarrassing myself with whatever's in my browser history. Balance projects. Got a service monitor. PCB. Okay, view image and view image. All right. Those diodes are not obvious which way the anode and cathode are. I should make that more obvious. Otherwise, that bottom looks pretty good. I mean, there's nothing there. What about the top? Artwork looks good. Dummy load. BNC antenna, SMA, BNC, SMA. Those BNC and SMAs may not be necessary. Antenna, radio, high Z tap. Minus 50 dB tap. 10K, 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 4.7, 47. Frequency counter, SIGGEN. Diode. Oop, hey! Where'd that K come from? Thinking about moving that forward up to the top. Oh, those are backwards from everything else. Let's fix that. Okay. So, edit. We'll do left justify. Put that the same direction as all the others. Okay, that's better. And what were some of the other ones I was looking at? So I'm thinking of putting that reverse up here, and maybe that forward up there. Errant K. Whoop, whoop, whoop. Nope, not that. Okay. Oh, hey, I got something else there. Oh, that's right. Okay. I'm going to make those more obvious which way they go. Do that on bottom silk. And just draw a line. Okay. So just outside that. Okay. Okay. Daughter's watching TV. Okay. Let's try this again. How much are these? 75 bucks. All right, so that's easier to read for the diodes. Okay, that's good. Straight through toroid, both. Okay. It just dawns on me. I've been doing a bunch of work off the side of the screen, haven't I? Oh, man. My OBS blocks off right about there, doesn't it? Oh. And probably on the bottom, too. Dadgummit. Do you even stream, bro? Anyway. All right. I'm pretty happy with this layout. I'm going to, for fear of not sharing my credit card information on the screen, I am going to order this off camera. But I think we've got a relatively good board for an RF deck. From here on out, the next thing I'm going to have to work on is the digital board. And I'm trying to figure out how I want to do that. I think I kind of want to use a Teensy. I haven't done anything with a Teensy before, and I've got a few of them laying around. So they're nice and powerful. They can do all kinds of things, and they got a lot of I/O if you're willing to kind of put some non-standard connectors on there. And they're Arduino compatible, which is always kind of a plus from a hackability standpoint. So I think I'm done for the day. Besides, it's been, I don't know, a couple hours. 73 minutes, so less than 2 hours. But it's getting lunchtime, so I'm going to go eat. And then I'm going to order these boards. Now, the good news is I have the entire week of Thanksgiving off. I've taken the entire week off, so I intend to be doing more projects during that week. Some of it may be cleaning up the mess of an office around me. I don't know if you can see how bloody disastrous my office is right now. But I have that whole week off, and I will be able, looking at the calendar now, I'll be able to get these boards ordered and delivered before Thanksgiving. So I should be able to assemble at least one or two of these and kind of test them out and see how they do and iterate on them. I will probably, assuming I don't get to it ahead of time, I will also start working on a digital board and figure out what I want that to look like, kind of the UI and the display and various other things. And be able to start putting this whole thing together. Thank you for watching. Thank you for joining me along with this journey of this QRP kind of service monitor. I got a lot of QRP radios that I don't know how to test, and so I'm hoping that this will help me put that together. So anyway, thank you very much for watching. Be good humans. Keep an eye out, and we'll catch you on the flip side. I'm KR6ZY. Be good humans. I already said that, didn't I? Anyway, I'm hitting the stop streaming button now. Well, I'm actually going to wait until my thumb pops up over there, because that's usually the sign. Actually, I'm going to do an end stream, waiting for the thumbs up. Has the thumbs up already come? Kind of the tail end of streams are always interesting in the beginnings, because there's a delay. There's my thumb. Okay, ending the stream.